Hello and welcome. Today I want to explain to you about multi-time step prediction or sequence-to-sequence prediction. But the output for this modeling is categorical data. So here in this Google Colab, I already defined the class, encoder, decoder, and the sequence class. And encoder decoder architecture is a common if you want to predict for case of sequence to sequence. And this is in this Google Colab, this is the most simplest form of encoder and decoder. And as you can see here in the encoder, I just doing the LSTM operation, and then for the decoder I also using LSTM, but after that I'm doing this linear operation, and then after that I'm doing the softmax. And as you know, the output for this encoder will become the input for the decoder. And yeah, the real output of our modeling is the output of the decoder. Okay, now I want to explain why the sequence to sequence prediction but in categorical data output is special. Okay, consider we want to predict a stock price, and this is just random. Just consider this is the random stock price graph. Usually, for example, in here I want to predict a 5 time step ahead of the stock price. So the general flow for the modeling will be like this. This is the input data. The input data in this case is the historical stock price data, and then those data is fed to the LSTM. We can use another model like categorical unit or ARIMA or anything else, but for this example I will doing the LSTM. Because we doing the encoder and decoder, I will make some correction. In my previous explanation, we can use ARIMA. We can just use LSTM and get categorical unit. And then after that, for the final operation, here I'm doing the linear operation, right? And then the softmax. For that, and for the softmax it will not change the depth of our output data, but that's why I will just show you the set of output for the linear operation. For example, I forget that. 5 times step ahead. Okay, so we will have 5 neuron here. 3, 4. Okay, this will be 3 plus 1, 2, 3, 4, 5. And as you can see here, the output for the linear operation will be resulting to this vector. This vector have a self 1 time if. But what if we, instead of stock price, we want to predict a weather? So weather, for example, it have many stats like sunny or cloudy or sunny but a little cloudy or rain. So here we have a forecast, and to represent this to the modeling, we must do a one-hot encoding. So for sunny, we will encode this to 1000. For cloudy, 0100, sunny but little cloudy will be 0, 0, 1, 0, and for rain it will be 0, 0, 0, 1. And if we doing the five time step ahead like the stock prediction case, we will have the output that have F4 times 5, and so it will have, oh yeah, 5 times 4 times 5, right? But as you know here, the output, because in this case we using the linear operation, and as you know, in my first explanation or previous explanation, I said that the linear operation will just outputting the output that have a set of vector like this, so it will be a vector, not a matrix like this, right? So how to do that, or how to predict the categorical data for LSTM in here? And to answer that, first I want to explain first how the LSTM outputting an output. Okay, so example, we have a LSTM here. This LSTM have a example, it have a hidden neuron as 20, layer, hidden layer as 3, and after that, yeah, just that. And then for example, we have a data set. For example, we want to predict weather, and to predict weather we must have relative humidity, temperature, PD, and etc. Another data. And yeah, consider for the data we have data here. We have a feature. Example, we have 7 feature, and then for the sequence length we will have 10. Oh yeah, in here we want to, for the sequence out, we want 5, right? And then for the class out 4. Okay, if we, oh yeah, I forget, for the batch size, example, we will have a 4, and if we outputting this data to the LSTM, we will have a output that have a set like, oh yeah, for the context here, I talk about LSTM in Python, okay? And we will have a type of data like 64, and then because, oh yeah, 10, and oh yeah, because we have a hidden neuron as 20, then the feature will be 22. But our target is here. We just want the 5 time step ahead, and the class must be, or the feature must be 4. That is where the linear layer, that is where we use the linear layer. Okay, now let's just see this in the perspective of single data. So we will have a data like this. And then to have a sequence out as 5, we must start this to this. We will just use the 5 plus sequence. Okay, so we will using the example 5, 6, 7, 8, 9, and 10. No. We just using 5, 6, 7, 8, 9. Remember in Python, the index is begin in 0. So yeah, this 9 is the last sequence. And we will use all the features. So step of this will be 5 times, no, 1 times 5 times 20. And then after that, instead of outputting or flatten this 5 times 20 to 100, and then outputting the for class here, we will not do this. Instead, we will do 5 times linear operation. So in here we have a 5 sequence, right? So and in every sequence we have a 20 feature, right? So the illustration will be like this. Consider this is a 20 feature, and this is the output neuron. We have a 4. Yeah, something like this. And this is in the perspective of one of the sequence, and because we have a 5 here, we will do this 5 times for every sequence, for every 5 plus sequence. So in the end, we will have a data set like 1 times 5 times 4. And if we include all the bets, we will have the set that 64 times 5 times 4. And then, yeah, that is how we do the multi-time step prediction for categorical data. Oh yeah, for the finishing, we will do the softmax. And yeah, this is the theory. Now, I want to explain that in the terminal. Yeah, I know I already built this Google Colab file, but I think the explanation in this terminal will be more understandable. Okay, first let's define our LSTM. LSTM, I forget the parameter for LSTM. Let's see, input size. Okay, the input size is the how many features we want to simulate in this whiteboard. So how many features is 7. And that hidden size. The hidden size must be 20. And then for the layer, 3. Oh yeah, in LSTM, layer mean is we stack the LSTM. So if I stack here 3 layer, it means the LSTM is we stacking the LSTM as 3 stack. Okay, you understand? Yeah, like that. So it's not like a multi-layer perceptron. It's just like LSTM that we stack them. Then after that, X, this is just random input. What we care now is just the shape of the data. Random number. Before. And the sequence is 10. The feature is 7. And oh yeah, the output of the LSTM will be a 3 component, that is hidden stat, L stat, and the real output. So we must do this to capture the output or the real output. Let's check the size this out. And as you can see here, same, like it have a shape that is that size, and the 10 in here is the sequence length, and the 20 in here is the hidden neuron in the LSTM. And now we will process this to the linear layer. Let's define our linear layer. The input feature is 20 because the output for the LSTM feature is 22. And then because we have a for class here, the output feature is 4. So output is oh, I forget the most important thing here. So I must redo this. We must define batch first as true because here the LSTM batch first, we must define this first because in the default the LSTM expect that the shape of the data is sequence times batch times feature. But you know that the batch in the first dimension, for me it make more sense. That's why I always activate this. Yeah, let's redo this. And then after that, yeah, the shape is same, but I think this is important. And then the auto. Oh yeah, I also forget about this. Oh yeah, we must start the data. So here we just using the four, yeah, 5 plus layers, so it will become like this. And no, 5 plus sequence. Yes, 5 plus sequence. And this is how we get the same exact output. Yeah, here we can get the output for the 5 times step ahead. This is the scheme that you can use. Okay, I'm sorry because there's a construction worker outside of my room, and in this recorder you will hear some noise. Yeah, now the last operation is softmax. Now I will show you why we want softmax. Okay, so here what we expect from this prediction, for example in here when we have a for class like this, what we expect is, for example, for sunny, what probability of the sunny, for example 20%, or cloudy 10%, or rainy 0%, or etc. But the output of the linear operation is something like this. You see here, this is a minus, and yeah, this is not a percent, so not a probability, and to change this to probability, you must do the softmax. And let's define softmax first. And then after that, we define dim as 2 because the probability is in the last layer. Let's check the output size first. You see the shape of the data is not changed, but output changed. And as you can see here, if we add all of this, we will get a value 1. And that's why we can treat this as the probability. And for the example here, for the sunny, we have a 19%, and for the cloudy, we have a 29%, and etc. And that is how this C-class works. And then after that, here I will explain. This is the last. I will explain how to train kind of game. And yeah, because this criterion because the calculation of the loss in the Python is expect 2 dimension and 1 dimension, 2 dimension for the output and 1 dimension for the label, we must accept that in the view like this. So we will have a output that is 2 dimension and the label that is 1 dimension. Okay, now we will ask why the label is in 1 dimension. Because the label in here, we just need to state what the class that for that label. So for example, in here, the biggest value is in here in the index 1, right? So the label must be 1. But if the biggest value in the last index or the index of B, then the label must be 3. And because of this, the memory usage will be more safe, right? Because we don't need to define the label as two dimension, right? Yeah, I think that's all. The rest is just doing the zero grad backward and step like this, like usual. Okay, see you in the next video. Bye.